Okay, so hello everyone. Today is day 11 of DSA problem solving. So the problems I solved were basically mostly on graphs, all were on graphs and based on famous algorithms. Okay, the first one was Dijkstra's shortest path, Prim's MST. Okay, it also is MST, minimum spanning tree, but using Kruskal's algo. Okay, bridges in a graph and articulation points in a graph. Okay, then there was Kosaraju algo. Acha, counting the strongly connected components. Great. And the final one was Bellman Ford algo. Okay, so I will go through each algorithm very slowly because I want to keep it and future use. Let's say if I want to just go through the similar type of problem, just I can watch it over. So in Dijkstra's shortest path, what we are doing? Okay, certainly we need a shortest path from the source to each node. Okay, starting from 0 node, keep track of the minimum distance to each node using okay set. Okay, we are using a set here, and along with that we are keeping a minimum dist and comma it in max. Okay, we start with 0 node in size. Okay, 0 0. Since we are using set, okay, so we added element to a set, get a front, check the neighbors, and we will use the condition, whatever condition, basic condition will be there, if else. And then okay, after updating we will check if you have to add this in a set. Okay, we will adjust the minimum distance. Okay, this is the thing to remember for me. Just let me walk through the code also. Let's say in future if I want to just go through a bit. Great. So next one is the Prim MST, which I think like you are creating a minimum search tree from 0 node, adding minimum weight node each time. Okay, so I remember. Just reading the line, you remember few things. Okay, so I will need a vector key vector, MST bool, and parent. Great. Now we have key, we have MST, we have parent. Key initialize with int max, then MST bool to when we are adding this to our actual MST, spanning tree, they will be parent. Okay, we have to do in 3 steps. We have first to get the mini from the key, and mini and the node from the key. Okay, and set MST is true for that node. Okay, since we are doing for 0 0 initially, from 0 we'll start 0 or 1 node, whatever that is. So we'll add this to the first time. Then we'll check for neighbors and we'll update the key and parent. Great, yeah. And finally we will the parent as answer. Okay, yes. You use the parent to get the answer, whatever which form it is asking. Just let me go through the code once. Creating the adjacency list, slicing key MST parent. Okay, 0 for 0 node. Okay, and times for n nodes. Okay, for the key we'll have to go for n times. There is no set. Okay, great. Get a mini from u, set MST is equal to 0, and finally the third part, updating the key and the parent, and finally use the parent to get the answer. Great. Then come the minimum spanning tree, Prim's method. Okay, I tried using Prim's method, almost solved 75% test cases, but got TLA later. We're just trying to use this concept. Okay, then Kruskal's algo. Okay, Kruskal's algo, we don't need adjacent list. Okay, so we keep it in the ascending order of the weights, sorting by weights on edges. Great. Okay, after that what we need? Okay, this was what we keep a function of parent node. Okay, basically let's say there's a tree, each node we basically assign its parent to our root node, whatever the root node we have, root node of that tree by recursion, and rank, think of rank vector. Okay, we need to think of that part also. And when we start, each node is its own parent, and we keep doing union. Great, this part important. Each node is its own parent and keep doing union. Okay, and this we need a function, basically recursive function for that, sorting. Let's start with from here. We did the sorting part. We have parent and rank starting with 0. We just need to update the rank file doing union part. Okay, so we have just made like this. Each node is parent of its own. From here, this function was this part is important, finding parent. So this was the recursive function. It will basically give the root node of that, like of that node. If you're asking, you're getting that there's a tree, and you're asking to give me the parent, it won't give you just the parent connected to it. It will give to the up to the last root node. Okay, find parents. Okay, this is the condition. UV if they are not equal. If they are not equal on if they are don't belong to the same tree. Here we see they are root. We got root node. They don't belong to the same tree. Okay, sum the weights. Okay, and then we form union. Union part is interesting. Let's see the union function. Union. Okay, you got those parents. If the rank is same, rank just add. So rank is different. So we just add one to another. Parent one to another. The rank is same. We can do anything. And rank plus one. Great. And this is just a compare we define to sort our adjacency list. Great. So we have this parent recursive function union set. Great. No adjacency list. Sort and using weights. Keep this recursive function and each most one parent and just keep doing union. Bridges. Okay, this one is a bit different. It was a trickier. I almost learned the entire part. Okay, we need disk and low vector and timer and visitor and use DFS. Need to handle package case. Okay, this part was package for the bridge, and while in the backtracking part we have to handle this part because we'll be updating the package. For package cases, low node will be updated, so we'll need to handle this because of this. Okay, if the parent it is ignored, counter plus plus. Okay, adjacency list. Initialize this with -1, then simply call DFS. When you're calling DFS, okay, there's the DFS. Great, yaar, I think it will go if I just remember the condition because thinking the conditions in the exam will be a bit difficult. Okay, let me go again. Adjacency list, initialize, just call DFS, and we have a counter, basically the timer part, and it's like counter plus plus. Basically, we have already visited it. Okay, we are going to neighbor is parent, is pass on. If it's not visited, okay, then visited, call DFS, do the backtracking one part, check for bridge, okay, and if it is already visited, then there will be a case of package. Okay, package case, update our low node. Great. So the articulate part is almost similar to the bridges one. Okay, so actually we have just got the solution from the video. So the condition changed a bit. Here is greater than equal to, and the parent is not equal to -1. Okay, the rest of the things were almost same. Okay, and for the root node, like where parent is -1, will count the number of child. If child greater than 1, okay, then this it is articulate point. Is like child 0 for this part, child plus plus. Okay, I have to think in that part when I solve it. Just remember there's a minor change from the bridge part in the article point condition, and also for the initialize for the 0 or the 1th node, whatever it is, we need to handle it separately using the child part, like counting that number of child. Great, we got from bridges, then we articulate, and this now the things a bit relaxing. Kosaraju algo. Okay, counting the strongly connected components. Okay, what are strongly connected components? Okay, it's the component, we pick a node and we keep traversing, and we can traverse to all the nodes in that component. Then it will call strongly connected. Kosaraju, this is a bit simpler. Do a topological sort, get transpose hoga, now do BFS. Okay, this is topo sort. We use stack here to do topological sort. We call it DFS function. Okay, adjacency list. Okay, topological sort. We define the transpose and simply we did the DFS. Okay, and we have count the number of components here. We returned it. This part is a bit simpler compared to the previous ones. 3-step topological sort, get transpose and do BFS. We want a topological sort, DFS, simple DFS, and essential list using static topological sort, transpose, and then DFS. We keep the count anchor to get number of components. Last one is Bellman Ford. Okay, so really here what we have to do, just focus what we have to do. Okay, this was also the minimum path, right? Minimum distance, minimum path, sorted distance to all vertices, and they basically the weights are negative here, so we can't basically use the Dijkstra's method. This one. Okay, so I come. Okay, so travel to, it's also it's sort of one. Travel to all edges and -1 times with the condition. This was a little simpler condition. This one. Okay, so basically, okay, we have traveled and we have kept a distance vector. We'll keep updating it. After we had -1 time, we will go for one more to check that is a negative cycle. And in the nth time, if there is a change in the distance array, though then there must be a negative cycle, then answer return -1. If not, then all good, return the distance. There's no change. Okay, so this is the part, this is the condition. Distance of that node plus weight should be less than distance of v. Oh, there was some, actually I was running this code, I got an error. Actually I was following the same entire code. I will check it out why I was getting the error, but the concept remains same. We have to travel the all edges and -1 times with this condition. Okay. Today become very lengthy. Okay then, that's it for today. Bye bye.